So where does the cosine rule come from, and why do they call it Pythagoras for all triangles? Well, let's first start by drawing up a triangle. Label it A, B, C for the vertices, and as usual, the side opposite the label with big A is little a, the side opposite the label with big B is little b, and the side opposite the label with big C is little c. As we did last time for the sine rule, let's drop a perpendicular from one of the vertices, vertex A, to the side opposite to it, and we'll call that H. Okay, now we've made two triangles. So this triangle down here, if I let that little bit in there be X, then what would this piece over here be? A minus X. A minus X. Why is that? Because that whole length there is A. So A minus X plus X adds up to that length of A. All right. So we've made two triangles. One, the triangle, that's where A is up the top. It's got little b, it's got little h, it's got x there, and full angle C. The angle A there, that's not fully taken through, it's just there for labelling purposes. So that's one of the triangles we've got, and the other triangle looks like this. It's got A minus X, that's B there, same H there, little c, and just for labelling purposes I'll put the A there, but it's clearly a different angle because it's been split. So there's our two triangles. I'm going to do a bit of the old Pythagoras' theorem on both triangles. I'm going to say that b squared equals x squared plus h squared. So rearranging that, I get the fact that h squared equals b squared minus x squared. I'm going to go across to this green triangle and do the same. C squared, the hypotenuse, equals a minus x squared plus h squared. So rearranging that, I get h squared equals c squared minus a minus x all squared. Maybe I'll expand this before I continue. That's c squared minus a squared minus 2ax plus x squared. I just used the normal expansion for a binomial to do that one. The next thing that I might do is just get rid of the brackets, minus a squared plus 2ax minus x squared. So I know that h squared equals b squared minus x squared, and h squared also equals all of that. So that means I can say that b squared minus x squared is equal to c squared minus a squared plus 2ax minus x squared, because they both equal h squared. I'm interested in this equality here, the blue and the green. What I'm interested in doing is seeing if I can eliminate anything first of all. Well, yes, there's a minus x squared on both sides. So if I plus x squared on both sides, I get b squared equals c squared minus a squared plus 2ax. All right, now x, what does that equal in terms of just the letters A, B and C? Well, I can look back up at this first triangle here and I can see that by trigonometry I can do cos of the angle C, and that's equal to the adjacent on the hypotenuse. Cos C equals x over b. I'll write that down here. Cos of C equals x over b. That's because we were dealing with this triangle, which I'll just bring back down into vision. Here, cos of angle C is adjacent on hypotenuse. Cos C equals x over b. Okay, so I can rearrange that. That means that x equals b cos C. So wherever I see an x in this equation here, because I only want to express it in terms of a's, b's and c's, but there's an x hanging around there, wherever I see an x, I can replace it with b cos C. So I'm going to do that. I've got b squared equals c squared minus a squared plus 2a, and instead of x, I put b cos C. And there's all little multiplications in there. That's basically the cosine rule, but let's write it down the way you would normally see it. Let's write it down with c squared as the subject of that equation. So, what I'm going to do is I'm going to leave c squared there, and I'm going to add a squared to both sides of that equation. So, if I leave the c squared alone and add a squared, it means there won't be an a squared on this side anymore, because if I add a squared on minus a squared, it'll disappear. So on this right-hand side, I'll just have that. But on this side, I've added on a squared, and I've got the b squared that I had before. So to get from this step to this step, I just added a squared to both sides. I want to get c squared by itself, so I'm going to minus that 2ab cos C. I'm going to minus this whole term off both sides of the equation. So over here, I'll just be left with c squared because I've minused off 2ab cos C. But on this side, I'll have a squared and b squared, and then I've got to minus off 2ab and times by cos of C. Now we normally would swap those sides left and right completely and see it written as c squared equals a squared plus b squared minus 2 times side A times side B times the cos of angle C. That is the cosine rule. The cosine rule could also be written a squared equals b squared plus c squared minus 2bc cos A. Or it could also be written b squared equals a squared plus b squared minus 2a, a squared plus c squared minus 2ac cos b. Now the interesting thing here, or something to note, is that the side and the angle opposite to it go at either end of the formula. If we're starting and trying to find side B, it'll be cos of angle B. If we're trying to find side A, it'll be cos of angle A. If we're trying to find side C in all of this, it'll be cos of angle C. You'll sometimes also see this formula written with the subject changed so that so that you can find an angle. I'll just write that down now for you. Sometimes people will have rearranged this so it says cos of C equals. Now cos of C equals a squared plus b squared minus c squared all over 2ab. That's another way it can be presented. If it's presented that way, it's still got that feature that the side and the angle opposite to it are at either end of the formula, so that can help you in substituting in the numbers. Another thing that's important to note about these two formulas So I'll put an asterisk here and an asterisk here. They don't actually find the side C straight on up, or the angle C, big C, straight on up, because this is C squared. So you still need to square root. And this is cos C. So you still need to shift cos in order to get the angle. So you can put all your numbers in and you still need to square root that side to get your final answer. You can put all your numbers in here, but you still need to then go shift cos to find C. So you've got to be careful with those formulas. Now, to answer the question, why is it that the cosine rule is sometimes called Pythagoras for all triangles? Well, consider what cos of 90 degrees is. Cos of 90 degrees is 0. So if you had a right-angled triangle and you're going C squared is A squared plus B squared minus 2AB cos, and it's right-angled, cos 90, this is 0. Cos of 90 is 0. And if you multiply anything, because these are all being multiplied by 0, this whole term here will be 0. And it'll wipe out that end term if your angle in the triangle is 90. So you'll be left with C squared is A squared plus B squared, which is your standard Pythagoras theorem, which works for a right-angled triangle. But this rule that we've found works for all triangles, including Pythagoras triangles, including right-angled triangles. It's just that this last term disappears with right-angled triangles because cos of 90 is 0. And that disappears the whole term and leaves you with what you normally see as Pythagoras' theorem. So now we have a formula that works for all triangles, including right-angled triangles, an overarching formula.